Hi friends, welcome to Follow Up. Let's have a look at today's daily challenge problem. Problem 931, minimum falling path sum. In this video, we're going to practice dynamic programming. So if you look at the problem statement, actually you should have a reaction that we might need use dynamic programming in this problem. So our purpose is to explain some detail, either use padding or not. So we'll quickly go over the statement and then digest one example, and then we do the coding. And we are going to present two formats of coding. So one without padding and one with padding. So we are also going to talk about in place and not in place, right? So now let's look at the problem statement. So this statement is very simple. We are given a matrix, a square matrix with number of rows or number of columns in. So we want to find the minimum sum of any falling path through matrix, right? So here you can see that. So a falling path is, for example, if you're currently at R and C in the position, then next you are going to go to the next row. Then either you can go left or you can go right or go downwards directly. That's the positions available. So here you can see the example. So it actually lists the 13, right? You can see 1, 5, 7, and 1, 4, 8. So, but in practice, when we do this, actually we think reversely. So we are going to look at one position. For example, I look at this 5 in between, in the middle, right? So how to arrive 5? We can arrive 5 from 2, and we can arrive 5 from 1. And we can arrive 5 from 3. But the minimal, if we arrive at 5, will be 1 plus 5, right? We're going to choose the minimal of the ones that can reach 5 from the upper row. So that's our strategy. So with that said, let's also quickly look at the problem size. So here, the matrix has a number of rows, a number of columns bounded above by 100. In other words, this problem is a small size problem because n square is bounded by 10,000, right? So now let's look at the strategy digest. So I'm going to use something like this. I'm going to use DP, right? Use a 2D table. So let's see RC. I want to denote this by the minimal falling path sum ending at RC. RC, right? So in general, if we want to arrive at this position, so we should consider the upper row. So the row actually is fixed, but there are 3 positions possible. One is from left, right? One is from right above, and then one is from right? Left, above, and right. So here C plus 1. But we want to consider this is always a valid index if R and C, we start from R from 1 actually, right? So this is always valid. However, C minus 1 may be less than 0 if you in the very left, like this 2 here, 6, you cannot consider negative 1. And the C plus 1 can be n, right? This is also out of bound, right? So with that said, let's look at coding. So I have changed the matrix to a capital letter A. This is just for convenience of writing. So here, what I'm going to do is like this. First, I'm going to write a solution in place. So without without padding. So now basically I want to modify the matrix itself, but the first row shouldn't be modified because there's no upper rows, right? So we are going to start from the second row. So let me write n is the number of rows. Then we are going to start from say for R in range, so 1 up to n, but not including. And then for position C in range, so we need to consider all positions, so we write n. Then we are going to first set, let's isolate this matrix element and RC, because we are going to override this position. So what we are going to do first, here we are considering R and C position, but this R is starting from 1. So this position, so R minus 1 C is always valid, or inbound. So this is based on our way of starting this R. So first, I'm going to set ARC to be temp, the current value, plus A R minus 1C. Then we are going to consider the left position, the right position. Overall, what we want to do is something like this. So we want dPRC to be the matrix at RC, then plus minimum of a dp, let's say R minus 1 and C, dp R minus 1, C minus 1, and dp R minus 1, C plus 1, right? But we need to check the validity of these two positions. So now let's do it one by one. So if C minus 1 is greater than or equal to 0, in other words, inbound, so we can further update this RC to be mean of the current state of RC, ARC, and then temp plus A R minus 1 and C minus 1. So that's the one. Yeah, actually you can think we also need to check another one, that is C plus 1. So for C plus 1, we require this guy is less than N to make it inbound. Then we're going to do this, R minus 1, so C plus 1. So this way we done the logic. And then we just need to return the minimal element in the last row, so A negative 1, right? So this actually forms a solution format to this problem. So we can do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So as you can see, the last time I do this is dating back to 2018, right? Yeah, actually, in the first try, I just read something wrong, right? So anyway, so I didn't pay attention to the index. So this is the version we want, right? So now let me write another solution. So for another solution, I want to do some padding. So this is just the technical details. Let me return to this one. So let's copy this part. I'll copy the whole solution. And I'm going to change this one to be version v1, right? So here I'm going to write is the not in place, right? So with pending, right? So what I'm going to do is first I want to pad the two sides, left and right, so that I can avoid to use these two ifs, right? So here what I'm going to do is I'm going to use a dp. Let's see, say float. Let's see, float positive infinity, because we don't want to come from these two positions. It's just a pseudo. So for this in range, so n plus 2, right? And then for another dummy index in range m, right? So this way, actually, we are going to get something like this. You can let me print out one first example. Yeah, I'm going to get something. Oh, I haven't populated the yet. So here we have this is the 5, this is the 4. Now let's see, Rn plus 2, right? And 2 n's. So now the size is right. Now let's continue writing the simple code. So let's populate the original solution. So for j in range 1 and the r plus n plus 1, right? So in other words, we don't consider the two n's in each row. So we're going to dp 0 j. The first row, it just does not change, so we just a0. So we're going to shift the index a little bit, right? So because we add two elements. So this way, let me print out this DP. So I'm populating this one, right? 1, 2, 3. So now let's update the DP table. So for the update, it's very straightforward, right? So for I in range, say 1 to n, right? So for j in range 1 n plus 1. Let's see. We are going to do is dpij, right? So it's going to be the current position in the matrix. So I. So notice that we want to shift, and then plus the minimum of the 3 from the last row. That is a. So say I minus 1 and j minus 1. This is always right, right? So this j is always right, and then a I minus 1 and j minus 1. Because we have appended from the left, this is always greater than or equal to 0. In other words, always in bound due to the range here, right? Because j is greater than 1, right? So now ai minus 1 and j plus 1. So the j plus 1, because here j is at most n, right? But j plus 1 will be at most n plus 1. But n plus 1 is a valid index due to here we add 2 elements. So now, with that said, we just need to return min dp negative 1, right? So this is another solution format, but here the obvious difference from the first version is that here we are not in place and with pending, right? But this is just some technical detail. It's good to know, right? So now let's look at the coding, the test. This is the outer bound. Let me check. So ij is so here 1 to n. There's 1 to n plus 1. So dpij ai j minus 1 plus. So this is I minus 1 j minus 1 the j plus 1. So I guess let's see dpij that would be ai j minus 1. This is right. Then plus min ai minus 1 j. So here it's not a because a is not SDP. Because a is set n by n, right? Now let's it passes the first example. So now let's look at the generic case. It passes all the cases. So I would see here we provide 2 formats of solutions to this, I would say, very straightforward problem. So actually, dynamic programming is a very classic and a very routine strategy to address some leetcode problems. Actually, if you practice more, you will find the pattern. So with that said, I guess that's it for this video. Thank you.